Okay, should I begin?
Yeah, please.
So hello everybody, I am happy to be a participant at this conference and thank you very much to the organizers for the kind invitation. I would like to talk about a class of algebras which are infinite dimensional, and this is based on a joint work with Sonia Natale and Blas Torresillas. I will work over an algebraically closed field K of characteristic 0, and all Hopf algebras will be supposed to have a bijective antipode. I start with the definition, which is already 30 years old, and I will not try to give the history of this definition in this moment. So the definition is what is a short exact sequence of Hopf algebras, or if you prefer, an extension of Hopf algebras, is a collection of 3 Hopf algebras A, C, B, with 2 Hopf algebra maps, iota and pi. We ask iota to be injective and pi to be surjective, and then there are 2 axioms expressing normality. One is that the kernel of P is the left ideal generated inside C by the augmentation ideal of A. And the other is, so this is a kind of algebra axiom, and there is a coalgebra axiom which says that the image of A under iota is the left covariant, sorry, the right covariance of P. And if you dualize, if A, C, and B are finite dimensional, you dualize, then these axioms interchange with each other, these last 2 actions. There is a special case which is more manageable when B is cocommutative and A is commutative. In such a case, we say that the extension is abelian. Now, under some conditions, one can say less about, you can ask, you don't need to check all the conditions. For instance, suppose that you have a Hopf subalgebra A or a Hopf algebra B, and let of Hopf algebra C, and let B be C divided by the right ideal generated by the augmentation. We say that A is normal if it is stable under the adjoint one or the other of the left or right adjoint actions of C. In case A is normal, then the left ideal generated by C is equal to the right ideal generated by A plus. So this is a 2-sided ideal. And if this happens, then it is a Hopf ideal, and B, which in principle is not in general is not a Hopf algebra quotient, will be a Hopf algebra in such a way that the map quotient map pi will be a Hopf algebra map. And this is what is important. If A plus C is equal to C A plus, and C is faithfully flat as a left or right A module, then the sequence is exact, meaning that the coinvariants of pi are A, and furthermore, A is normal as before, and pi is faithfully coflat. So this is one possibility, and the other possibility is the dual one, namely you start by a surjective Hopf algebra map, pi, and take A, the right coinvariance of pi inside C. Then we say that B is conormal if the kernel of pi is a subcomodule for the adjoint coactions. If pi is conormal, the left coinvariants coincide with the right coinvariants. And in such a case, A is a Hopf subalgebra of C. Furthermore, if C is a faithfully coflat B commodule, then the exact sequence A, C, B is exact. And furthermore, iota is faithfully coflat also by itself. There is a special case when this special setting of these extensions of Hopf algebras is when the extension is cleft. The extension is cleft. I need this definition later when there exists an invertible map of B comodules from B to C. And this is equivalent to have an invertible map of A modules from C to A. If R, the notion of cleftness is more general, available for right H commodule algebras. For instance, if you have a right H commodule algebra, you take the right covariance, and then you say that this is cleft if there exists a map chi as before. And there is a technical lemma, which I will not explain in detail, due to Doi and Takeuchi. An extension of right commodule algebras is cleft if it is H-Galois and has the normal basis property. The example that we will use later is that is a remark by Ulbrich saying the following: if you have a group G and R is a KJ commodule algebra, this is equivalent to say that R is a G-graded algebra, and saying that the R is a H-Galois over the coinvariance. The coinvariance is the homogeneous component corresponding to the trivial element, to the unit. Then this is H-Galois if and only if the grading is actually strongly grading, meaning that RG-RH is exactly equal to RGH. Well, there is a remark when this was observed by several authors, when the extension of Hopf algebras ACB is cleft, then C can be reconstructed from A, B, weak actions and weak cocycles. This is very complicated, and actually it was never applied to build any example, except in the abelian case. So the abelian case is very useful, but otherwise it's not useful. Now, mimicking what the vocabulary for groups, let us say that two Hopf algebras, suppose you have two classes of Hopf algebras, D and A. Then I will say that a Hopf algebra H is in the class D by A, or simply that the H is D by A. If there is an exact sequence as before of Hopf algebras, DHA, where D in D in the class D and E belongs to the class E. For example, H is commutative by finite if there is an exact sequence A iota inside H and projected by P over U, small u, where it is assumed that A is commutative and the dimension of U is finite. And Cartier proved, since we are assuming characteristic 0, in 62, that any commutative Hopf algebra is of the form O of G, so the algebra of regular functions on G, where G is the group of characters of A, and this has a structure of a pro-affine algebraic group. Therefore, in view of this theorem, if you have a commutative by finite Hopf algebra, this means that there exists a pro-affine algebraic group G, such that OG is included in H, and H has a projection to small u, which is finite dimensional. Let me give some examples of commutative by finite Hopf algebras. Suppose that you have an algebraic group G, which is simple and simply connected. Let small g be denote its Lie algebra, and this Lie algebra by hypothesis decomposes as n plus direct sum h direct sum n minus for some choice of a Cartan subalgebra H and for some choice of positive roots. And I will call S the direct sum of B plus with B minus, where B plus is n plus direct sum H and B minus is H direct sum n minus, divided by H, which is included diagonally in some sense inside B plus direct sum B minus. Then I take a group GD, which is such that the Lie algebra of GD is the algebra S I just described. In terms of Poisson-Lie groups, GD is the Poisson dual of G. Now take L, an odd positive number, which is coprime to 3 if G is of type G2. And take epsilon, a primitive root of unity of order L. So the examples I want to mention are the quantized enveloping algebra of functions O epsilon of G at epsilon, I repeat, is the root of unity with some constraints. And this quantized algebra of functions was defined in some case by Manning for AN and in general by Lustig. And it can be shown that this is a cleft central extension of O of G by the dual of the finite quantum group U epsilon of G. So this iota can be thought of as a kind of Frobenius map, if you wish. Then there is, from this example, there is another example, which is the classification of the quantum subgroups or quotients of O epsilon of G. And it turns out that these are extensions of L, H, M dual, where L is inside G and M is inside U epsilon of G. Another example coming from the theory of quantum groups is the de Concini-Katz-Processi quantized enveloping algebra U epsilon of G. This is a cleft central extension of the algebra of functions on GD, where GD is the Poisson dual that has the algebra S, as I mentioned it just before. Generalizing the examples by the Concini-Katz-Processi, Anchiono introduced the Drinfeld doubles of some objects called distinguished pre-Nicolás algebras of diagonal type. And they are cleft central extensions if you assume that the parameters have some specific shape. So this is about examples of commutative by finite. Now I go to another example of this kind of denominations, which is finite by cocommutative. So finite by cocommutative, as I said before, will mean that there is an exact sequence A inside H projected to U, where A now is finite dimensional, so now the finite is at the beginning, and the quotient is cocommutative. Examples of cocommutative Hopf algebras are, of course, universal enveloping algebras and group algebras. So our first example of finite by cocommutative is the Lustig quantized enveloping algebra U epsilon of G, which is not the same as the de Concini-Katz-Processi. In particular, it is finite by cocommutative because it contains now U epsilon of G instead of projecting to epsilon of G. And the quotient of the quantized enveloping algebra of Lustig by the small quantum group is U of G, the universal enveloping algebra of G. So this is finite by cocommutative. Recently, Brown started to study together with Couto and Jaén, they started to study the finite dual of a commutative by finite Hopf algebra. And they show that this is finite by cocommutative. In a paper written some 10 years ago with Juan Cuadra and Pavel Ettingov, we show some examples of co-Frobenius Hopf algebras which are finite by cocommutative. We found these examples trying to disproving actually a conjecture made by Sorin Dascalescu and myself 20 years ago. And Li and Liu described some finite duals in independent work to Prom-Kauto and Jaén. They described the finite duals of some Hopf algebras of Gelfand-Kiel of dimension 1. And as a matter of fact, the examples of Li and the examples by Cuadra, Ettingov, and the speaker. Okay, so this was a reminder of extensions of Hopf algebras and of the classes of finite commutative and commutative by finite Hopf algebra, classes of Hopf algebras. Now I would like to present some families of Hopf algebras arising from a Hopf algebra with a central Hopf subalgebra. So I start with an Ethereum Hopf algebra, H, and a central Hopf subalgebra, A, contained in H. Then, by a result of Hans-Jürgen Schneider, H is faithfully flat as A module. And of course, if it is central, it is normal. What I do not know is if A is Noetherian in this case. So from the Noetherianity of H, does it follow the Noetherianity of A? Anyway, I take as before, as in Cartier's theorem, G as the group of characters of A, and A plus, as usual, is the kernel of the counit, the augmentational ideal of A, as I already mentioned it. And as before, as in the general setting, I consider H epsilon as the quotient of H by HA plus. HA plus, since A is central, is a two-sided ideal, so by the theory I already expanded, this gives rise to an extension H epsilon. More generally, one can consider for any character kappa, that is for any element kappa of the group G, the quotient of H kappa by the ideal inside H generated by the kernel of kappa. Now I will consider inside the category of finite dimensional H modules, which I denote by rep H, I will consider a specific subcategory C, which consists of objects where our algebra, our central Hopf subalgebra H acts in a semi-simple way. In other words, if V belongs to C, if V is belong to the category C, then V is a direct sum of V kappas, where V kappa is the isotypic component of type kappa. Furthermore, I consider the algebra, the subcategory of C kappa, consisting of those objects V, such that V is equal to V kappa. In other words, we have a grading of the category C as a direct sum of all subcategories C kappa, where kappa is in G. Now, in general, I will denote by CV the coalgebra of matrix coefficients of a finite dimensional representation V. That is the image of the, if rho V from H to end of V is the finite dimensional representation, I transpose rho V, and this gives us that the image of this transpose of rho V is a subcoalgebra of the finite dual or Sweetler dual of H. So now I put together all matrix coefficients, coalgebras of all V in C kappa, in this subcategory which I mentioned before, that consists of all V's equal to V kappa. So C kappa is a subspace in principle of H dual, but it is easy to see and fairly obvious that this is really a subcoalgebra of the finite dual H0, and this for any kappa in G. And now this is the crucial point of our construction. I take any subgroup gamma of G. So G is algebraic, but I do not ask G to be algebraic, so it could be any subgroup. And I define a category C gamma as the direct sum of all C kappas, but where a kappa belongs to gamma. Since gamma is a subgroup, this is a tensor subcategory of RIP of H. Therefore, I will take H gamma as the direct sum over all kappa and gammas of the subcoalgebra C kappa that I mentioned it in the previous slide, that I introduced it in this previous slide. And it turns out, since gamma is a subgroup of G, that H gamma, calligraphic H of gamma, which is a direct sum of all C kappas with kappa and gamma, is a Hopf subalgebra of the finite dual H0. In this way, C gamma is a category of comodules over the Hopf algebra H gamma. The Hopf algebra H gamma is our main object of interest in this talk and in this paper. Now I consider the subset of gamma consisting of those kappas. So for any kappa in G, I introduced an algebra H kappa before as H divided by the ideal generated by the kernel of kappa, and I look at those kappas in gamma such that the category of finite dimensional representations of H kappa is non-trivial. And this is the same as the kappas in gamma such that C kappa is different from 0. This is a subgroup of gamma, but could be strictly smaller than gamma. There are cases where kappa has no finite dimensional representation, except the trivial one. So I say different from 0, I should have said different from K. Okay, anyway, the theorem that we have proved with Blas and Sonia is that the sequence H gamma projects onto K of gamma FD, and the kernel is the finite dual of the Hopf algebra H epsilon that I introduced before. Then we proved that this sequence is exact and that H gamma is faithfully coflat as K of gamma FD comodule. Now, before going on, the next goal is to show some properties of this Hopf algebra H gamma in this generality. So before going on, I would like to remind some definitions of Hopf algebras. The first is a Hopf algebra is cofrobenius if there exists if it has a left or right integral that is, if there is an element of the dual which is non-zero, which is I denoted by small integral, which is invariant under the dual of the left regular representation. It is known that K is cofrobenius on the left if and only if it's cofrobenius on the right. And there are a lot of good homological properties of cofrobenius Hopf-algebras concerning the category of comodules. A more precise, a more restricted notion is the notion of cosemi-simple Hopf-algebra. This is a Hopf-algebra is cosemi-simple if the category of K comodulus is semi-simple. And this is equivalent to the fact that K is the direct sum of the matrix coefficients of the simple comodules. So it's a kind of Peter-Weil theorem. And this was shown by Swidler many years ago, that is equivalent to be cosemi-simple, that to be cofrobenius, and the integral on one is any non-zero integral on one is different from zero. In fact, if K is cosemi-simple, the integral is the projection onto the coalgebra the coalgebra of matrix coefficients of the trivial representations. The projection according to this is the composition to this direct sum. Okay, some examples of cofrobenius and non-cofrobenius and cosemi-simple and non-cosemi-simple Hopf-algebras. First, if the dimension of K is finite, then K is automatically cofrobenius by an old result by Larson and Swidler. And it's not always cosemi-simple, because by Larson-Radford it will be cosemi-simple only if K is semi-simple. If K is semi-simple. The enveloping algebra of Lie algebra is never cofrobenius. Any group algebra is cosemi-simple. Well, this is a pretty obvious statement. And if you look at the algebra of functions on an algebraic group, then Sullivan in 71 proved that K is cosemi-simple if and only if is cofrobenius, if and only if the group is reductive. If you go to quantum groups, if G is semi-simple Lie algebra, then any of these quantized enveloping algebras UQ of G could not be cofrobenius. And if you have a look at the dual algebra of matrix coefficients of OQ of G, the quantized algebra of functions on the group G, then K will be cofrobenius always, but it will never be cosemi-simple only if Q is not a root of unity. In another paper with Juan Cuadra, we proved that if you have an exact sequence of Hopf-algebras such that C is faithfully coflat as a B comodule, then C is cofrobenius, respectively cosemi-simple, if and only if A and B are cofrobenius, respectively cosemi-simple. So looking at the extension that I mentioned before of H gamma as extension of H epsilon finite dual by the group algebra of this group gamma FD, we conclude immediately that H gamma is cofrobenius if and only if H epsilon finite dual is cofrobenius, and same for cosemi-simple. Furthermore, if the dimension of H epsilon is finite, then H gamma is cofrobenius, and it is cosemi-simple if and only if H epsilon is semi-simple by the Larson-Radford theorem I mentioned in the previous slide. Okay, so this is a very general construction, and what we could have said about them is in the previous slide. Now I go to a class which is much more restricted. It starts again by the same input as before, so it is a restriction of the previous construction. H is an Athenian Hopf algebra. A is a central Hopf subalgebra of H. And G is the group of characters of A, exactly as in the second part of the talk. And we will assume now that two more conditions. So everything as in the previous part, but we assume that the dimension of H epsilon is finite and that the extension H epsilon is cleft. Under these conditions, immediately one concludes that H is a finitely generated A module, that H epsilon finite dual is just the dual. This is because the dimension is finite, and also that the group gamma, the subgroup gamma FD of gamma is actually all of gamma. And using the cleftness, we can prove that the dual exact sequence H epsilon dual H gamma K gamma is again cleft. In particular, this shows that H gamma is strongly gamma graded by the result of Ulbricht and by Totoya and Takeuchi, because cleft implies H Galois and H gamma implies in this case that it is strongly graded. Now, H is a finitely generated A module, then since H is Noetherian by a classical result by Formanek and Jatega-Onkar, A will be Noetherian, and by Molnar this will imply that A is affine, meaning that it is finitely generated, and therefore the group G is not a affine algebraic group, it's an affine algebraic group without the pro. Let me say that the group is linear if it is embeddable into GLNK for some n. In particular, since gamma is a group of G and G is an algebraic group, gamma is linear. By the Tits alternative, if you have a finitely generated linear group, either it is solvable finite or it contains an abelian free group. I will use the theorem of Tits immediately in the next slide. Before, I would like to say that I would like to stress what I used before. I will say that an algebra is affine if it is finitely generated. In general, it's not a very restrictive assumption, because tensor algebras and group algebras of free groups are affine. Groups of finite sets. Now, it is easy to see that if gamma is finitely generated, then the algebra H gamma, which is in the previous slide, is finitely generated. It's affine. Now, I go to the next question I would like to understand is when the Hopf algebra H gamma, under the conditions already mentioned, has several properties, several algebra properties. And the first property is finite Gelfand-Kirchhoff dimension. Let me recall that the Gelfand-Kirchhoff dimension of an associative algebra A is given by this formula, the sub over all finite V's, finite dimensional V's of this slim sub of log n of the dimension of K of Vn, where I assume that 1 belongs to V. If A is commutative, then the Gelfand-Kirchhoff dimension of A is the Krull dimension of A, which is the dimension of the maximal spectrum of A. And if G is a Lie algebra, then the Gelfand-Kirchhoff dimension of the enveloping algebra is the dimension of G, which could be an integer or infinite. Another example of Hopf algebra with finite Gelfand-Kirchhoff dimension is a famous result by Mikhail Gromov, 81, says that if you have a finitely generated group lambda, then the Gelfand-Kirchhoff dimension of the group algebra K lambda is finite if and only if lambda is nilpotent by finite. where nilpotent by finite is, as expected, it has a normal nilpotent subgroup of finite index. Now, in our setting, if gamma as above inside G is finitely generated, then the Gelfand-Kirchhoff dimension of H gamma is finite if and only if gamma is nilpotent by finite. And in fact, the Gelfand-Kirchhoff dimension of H gamma is the Gelfand-Kirchhoff dimension of K gamma. This is because the difference between H gamma and K gamma is a finite dimensional Hopf algebra. What about Noetherianity? Recall that an algebra is Noetherian if it satisfies the ascending chain condition on left ideals. Let me tell you what is known about Noetherianity of Hopf algebras in the classical case. If G, here they are very classical open questions. For instance, if G is a Lie algebra, then the dimension of G is finite, of G is Noetherian. But the converse is open. So it is not known if an infinite dimensional Lie algebra has an enveloping algebra which is not Noetherian. The more recent result I know about these questions is by Susan Sierra and Chelsea Walton. They proved that the universal enveloping algebra of the Witt algebra is not Noetherian. In characteristic 0, a commutative Hopf algebra, say A is a commutative Hopf algebra and G is the algebra, the group associated group of characters, then A is Noetherian if and only if A is affine, and this implies that the Gelfand-Kirchhoff dimension of A is finite. And this is classical, the equality between Noetherian and affine is classical, but what is not true is that the Gelfand-Kirchhoff dimension is finite implies that A is affine. For instance, take the group algebra of any suitable group, which is a union of finite subgroups in some sense. For groups, the Noetherianity is an open problem. Let me say that the finitely generated group is polycyclic if it is solvable and every subgroup is finitely generated. This is equivalent to say that it admits a subnormal series with cyclic factors. A classical old result by Hall is that the group algebra of polycyclic bifinite group is Noetherian. And there is a classical conjecture that if a group algebra is Noetherian, then lambda should be polycyclic bifinite. If K lambda is Noetherian, then the group is Noetherian, meaning that it satisfies the maximal condition on subgroups. But there exist Noetherian groups that are not polycyclic bifinite. However, their group algebras are not Noetherian. However, for linear Noetherian groups, because of the Tits alternative, they are polycyclic bifinite. And to prove this, using this, we proved the theorem about the Noetherianity of our Hopf algebras H gamma. That is, H gamma is Noetherian if and only if gamma is polycyclic bifinite. One implication is clear. If H gamma is Noetherian, K gamma is a quotient of H gamma, and then it is Noetherian by the Tits alternative and the previous result. And the converse uses an old result by Năstăsescu and Van Ostiayen. And actually, this gives many examples of H gammas that are Noetherian, because Auslander and Swan proved that any polycyclic bifinite group is linear. This leads us to several questions in the theory of Hopf algebras. The overall question is to classify affine Hopf algebras with finite Gelfand-Kiel of dimension or with the Darnetherian. Actually, it's not clear to me what is the right notion of algebraic quantum groups, whether it is finite Gelfand-Kiel of dimension or Noetherian, or something in the middle. It is known that the subalgebra of an Noetherian algebra does not need to be Noetherian, and therefore to implement any method to classify Noetherian Hopf algebras starts with some problems which are difficult to handle. For instance, there is a question whether the bosonization of a braided Hopf algebra, which is Noetherian, by a Noetherian Hopf algebra is necessarily Noetherian again. This is open. Another question is, if you have an affine Hopf algebra, this is by Brown and Gilmartin, if given an affine Hopf algebra, affine, I recall, means finitely generated. If it has finite Gelfand-Kiel of dimension, it is true that H is Noetherian. This I do not know. It's not in all the examples we know so far. This is true, but it is hard to prove. At this moment of knowledge, we do not know how to prove this. Another question by the same authors and independently by Zhuang is that given an affine Hopf algebra, whether the Gelfand-Kiel of dimension of H is necessarily an integer or infinite. Again, all examples point towards this, but no proof is given. Another property of Hopf algebras that we would like to understand about H gamma, whether it happens that it has this property, is regularity. By regularity, I mean Noetherian plus finite global dimension. For instance, if G is a finite dimensional Lie algebra, then U of G is regular. If lambda is polycyclic bifinite, then K lambda is regular. And the algebra of functions on an algebraic group is always regular. There is a classical lemma which says that a finite dimensional Hopf algebra is either semi-simple or it has infinite global dimension. And this follows, in fact, this holds for any finite dimensional Frobenius algebra. So it's just a consequence of the fact that any finite dimensional Hopf algebra is Frobenius. Schneider proved some time ago that the Hopf algebra is free over any finite dimensional normal Hopf subalgebra. And from this theorem of Schneider and the previous lemma, it follows at once that a Hopf algebra K with a finite dimensional normal non-semi-simple Hopf subalgebra could not be regular. And as a consequence, H gamma is regular if and only if gamma is polycyclic bifinite, which is needed for Noetherianity, and the finite dimensional algebra H epsilon, which I mentioned before, was one of our inputs, is semi-simple. And this happens because H epsilon dual is contained in H gamma as a normal Hopf subalgebra. Now, there is a hierarchy of problems on Hopf algebras with finite Gelfand-Kiel of dimension, whether they are domains, primes, semi-primes, primitives, or semi-primitives. And there is a bunch of questions about them. It's really, in many directions, we are ignorant of what happens. However, I would like to mention a question by Scriabin. If you have an Noetherian Hopf algebra, which is a domain, is it true that it is semi-primitive? So semi-primitive means that the Jacobson radical of K is 0. In general, it's not true that the domain is semi-primitive, but for Hopf algebra, it is open. And I think this is a very interesting question. For instance, for Lie algebras, U of G is a domain and U of G is semi-primitive. If you have a group lambda, then K lambda is a domain, but implies that lambda is torsion-free and implies that K lambda is prime, but the converse is an open question, a famous open question by Kaplansky called the Kaplansky of the zero divisor conjecture, meaning if lambda is torsion-free, it is not known whether K lambda is a domain. In characteristic zero, every group algebra is semi-primitive because, in particular then in semi-prime, because provided that K does not contain the rational numbers. If K, provided that K is different from the algebraic closure of Q, of the rational numbers. This is, I learned this theorem recently, and I am surprised that you cannot answer this question for K equal to Q bar. There are group algebras that are primitive, and there is a theorem by Connell that characterizes when the group algebra is prime. The group algebra is prime if the FC center of lambda is a torsion-free abelian subgroup, and this is equivalent that there are no finite normal subgroups except the trivial one. Okay, so this is the kind of questions I am interested in: how to classify Hopf algebras with finite Gelfand-Kiel of dimension, or Noetherian Hopf algebras. It already, for the classical examples, this seems to be very complicated and very difficult, and the family H gamma provides examples and counterexamples to these properties, as I explain it in this talk. Thank you very much for your attention, and I finish here.